Okay, welcome to a video on the Libre-SOC Dependency Matrices and computational units. These are based on the 1965 CDC cyber computer control data computer 6600 by Seymour Cray and James Thornton. And with the help of Mitch Alsop, we've been able to augment that to precise, exception capable and multi-issue capable. So here is a translated version from the original book by Mitch Alsop in a couple of book chapters which he added. One important thing is that sorry Mitch, you missed something important, which was this read request signal. So just to go over this, you have an issue, go read and go write, which cycle through, so only one of these is on at any one time. And so, but one other thing to note about this is that the original diagrams and the ones that Mitch is doing, for original diagrams from Thornton's book, Design of a Computer by James Thornton. You can find a copy online, by the way. They depend on high and low clocks, so that becomes significant later. So you have some signals captured on the high clock and some captured on low. We won't be doing that. We're modifying the diagrams, but we're leaving, for the purposes of explanation, we're leaving the logic as it was from the original. So first thing you notice is that you get the issue signal comes in, and these are, yes, these really are SR latches. They are not D flip-flops. There's actually no clock signals coming in on these. It's purely relying on the issue, go read and go write. So issue goes high, which is on the busy signal, and because this is a cycling system where go read brings both operand 1 and operand 2 in, there is only that, the logic is greatly simplified, so it's literally going this one, that one, that one, that one, that one, that one, this one, that one, that one, right? So busy goes high, but also you can see it goes to read release as well. All right, and this is the bit that was missing from Mitch's book. This gets turned, issue will be initially off. So busy comes in, and he is off. That actually, I suspect that is wrong. That should be onto this signal here, because otherwise this can never go on. Right, it needs to be issue, which then triggers read release, which indicates that go read may be set to high. Following that, when the go read goes high, this goes on, which, because that comes from there and from that, when that goes high, this will go on because it's an SR latch. So, squiggle, squiggle, squiggle. Alright. There we go. Right, brilliant. Okay, so issue goes high as the first signal, which also sets this to off, which tells us that the read release goes on. When read release goes on, then the dependency matrices, etc., know that go read can be triggered. When go read gets triggered, that this goes in, so that goes off, so read release is dropped. Hooray! However, go read also comes into here, which sets this to on, and because busy is still set, because we haven't had a write yet, busy is still set, and request release is set. Now this is a term, here there's a little diagram here of a timing chain, which basically, the note here is timing chain that matches computational block latency, because you've latched in operand 1 and 2, because that went go read, that went thing. So whatever was in here, when that went low, operand 1 and operand 2 were latched in. So however long this computation takes, you need to have a matching delay on here, such that blah blah 1, 2, 3 clock cycles, bink, request release, this result here is ready, this in this data in here is ready, and request release, this was off, and you have a request release, you have a following cycle, you have a go write, which will switch that off, that will latch that in, and it also goes into the busy, into this SR latch, which switches that off, and now that will no longer be busy, and the request release will be dropped. Hooray! Alright, so issue goes on and then off. Read release signals that go read may be done. Request release says that the go write may be done. When go write is done, this latch is off. So it's this one on first, and it stays on. Then this one goes on when that thing. Then this one goes on and that one goes off when that thing. And then finally that one goes off and that one goes off, and you're back at the start again. All right. So despite the fact these are SR latches, the external logic linking these and these guarantees that these SR latches will never go into the unstable state. At no time will these signals change simultaneously on there, or there, because there's this revolving door system between them. All right. Now, the next bit is let's zoom out. Okay. I'd like to bring this up a little bit higher, or have made this a bit smaller. Never mind. I apologise. Okay. 1, 2, 3, 4. That's the new diagram that we're doing. So let us ignore this top portion here, okay, for now. That's my error diagram. We want this one. Yeah. Okay, so the problem with this is that it assumes that there is only one go read for both operands. Therefore, if you have both read ports on the register file have to be available at the same time. And as we're doing Power 9 architecture, we need three inputs and 2 outputs, and therefore having to do this. So while this was previously issue, go read, go write, and issue, read, release, go read, request, release, go write, we're having to do issue, read, request 1, 2, and 3, go read 1, 2, and 3. Only when those 3, in any order, where each of those is associated with the operand 1, so read request 1 is associated with operand 1, 2 is read request 3 is associated with operand 3. In any order, these can be fired, but when all 3 of them have fired, and that's what this that is for. When all 3 of them had fired, only then can we move to the next phase, which is the write request 1 and go write 1, and write request 2 and go write 2. So let's go through it. So you've got issue, then all these 3 set SR latches are switched on, which in combination with the busy signal ending in from here, with the fact that each of 1, 2, these 1, 2, and 3 are set, so Q is set to true, all 3 of these read request signals will go true. And that will feed back into the dependency matrices, which will do a priority picker and will fire any one of, on the next cycle, will fire any one of go read 1, 2, or 3, or all of them, or 2 of them, or none of them, in fact. So when that happens, depending on which one fires, etc., the reset will be fire triggered on the corresponding SR latch, which will tell it to drop. Now, unlike in this diagram, where that go read, because there is only one of them, you guarantee that the next phase can proceed straight away. So that's why you have the go read signal going into there thing. So enable dunk, that sets up the read request. So once that go read goes in, you know for a fact that you're going to get a go write or request a go write afterwards. That is not the case in this one. You must have all 3 of those triggered before the write request can proceed. So consequently, your busy comes in here. So only when you are busy and when all 3 of these read requests are false will the write latch system, which we're going to zoom into, will the write latch system start to trigger. So you have 2 separate write requests, and actually I redid it as a diagram down here. And here's one I prepared earlier. Okay, so this is write request. This is go write 1. That's go write 2. That is request 1, and that is write request 2. And this is go 1, go 2. Go. So you need 3 SR latches. 1 for, okay, so this is when the go reads, all go reads have completed. and it will pull a set and pull the Q high on the write request 1, and a separate one pulls Q high on write request 2 latch, which again, when that goes low, it indicates to the register that it is to latch that result. Okay, so this is a register. This is a symbol for a register. So what's that signal? That's shadow. That is the signal which deals with precise exceptions. When that's high, it prevents all the writes. So you can, and only when you're accept the opportunity for damage to the state, the register file, etc., the opportunity is cleared. In other words, it is safe to commit. This shadow flag will be pulled low, and that will enable, because there's a knot on here, that will enable there and there. That will enable those writes to proceed if they are in fact high. So we get that. It's an important thing. That's one of the modifications that Mitch also very kindly explained to us how that works. It's the one thing that was missing from the 6600 is that there was no write commit exception handling. So notice there's this third one here as well. So again, just as with this mirror here, we've mirrored this multi-knotting thing down here as well. So this is equivalent to that busy signal. The busy signal into the things here. All right. So we've got these three latches, and only when both of those write requests have been acknowledged with their corresponding go write and go write 1 and go write 2, will these both go low. Consequently, because this is high, this is Q is set on here, and both of those writes are low. When they're inverted, you get an and that indicates your reset signal to say, hey, we're done, guys. That goes back. That signal is the one that that is this here. I've replaced this bit with that lot. That's the signal that goes in and says issue is to be reset, and busy goes off, and this computation unit is ready for reuse. Phew. Yeah. So again, just a recap. Unlike this diagram, where you've got this very simple 1, 2, 3, and the assumption is that once you've done a read, you may proceed immediately to write. Apart from that delay kind of thing there, which is associated with the length of time that this takes. This can, by the way, just be just a timing tree with some SI latches with a clock signal going in, and you chain them together, dunk 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 kind of thing. That's the normal way it's done. That's how it was done in the 6600. Well, that's very, very, very simple. This one instead has to have that break between the read side and the write side, and only when all reads are completed can you proceed to permitting any write requests to be active, and only when all write requests have been acknowledged can you go to pull the reset line and go back to the thing. Now, where is... I really should have pointed out the other diagrams. I apologise. Have I got one? No, I haven't. Rats. I'm sorry. Right. So this one is dependency matrix cells. So basically, for this one, you only have the go read and go write, and read request and read release and request release. Whereas for this one, you have multiple go writes and multiple go reads. So the purpose of the dependency matrices is to identify the read after write hazard and the write after read hazards. And now that there's multiple of those, we can't just OR things together and saying they've got to be separate signals. So what happens is you have an issue coming in for these are your register numbers. Okay, so this would be register 1, this would be register 2, register 3, etc., etc. So this indicates whether that is for operand 1's, register 1 is to be used for operand 1, and register 2 would be used for operand 2. It would indicate that this wire would be pulled in the cell next door. It's function unit, so this is a block for function unit 1, okay, which would be this baby. Function unit 2 would be below it, function unit 3 below that, etc., etc. So it's a pretty big matrix. If you've got 32 registers and say 20 function units, you have a massive 32 by 20 matrix, and that's where these OR gates comes in to OR the register select lines down here. So what you need to do is you need to preserve an indication for each register file port, an intention to use it and access that thing. So this is for register write port, register file write port 1, this is register file write port 2, read port 1, read port 2. Then on the next cell, write 1, write 2, read 1, etc. Going down. All right. So this cell says, this SR latch, when you have an issue coming in, that is your instruction issue, will, if you want to use operand 1, and so to register 1, this as a read, operand 1, sorry, as a destination, as a write, because that's there, that's a destination, so this is the destination 1 line down here, destination 2 line, operand 1 read line, operand 2 read line. So destination, excuse me, there we go, that's better. By destination 1, not that, okay, need some Tipex. So destination 1 on issue if this do this again, you have an instruction which needs register 1 for its destination 1, this SR latch, the Q will go high. Then, if this is high, it stays high such that on subsequent operations, if ever another instruction requests a read on this same register 1, whether that register be in operand 1, that read be in operand 1 or operand 2, this OR gate will activate. You can see that comes into this AND gate here. This OR gate will say, going out, that there is a read after write hazard. In other words, once that is locked in, it protects register 1 from writing by any other read. Okay? But because there are two potential registers being written to, we need to protect the we need to or both of these things. So if there are two destination registers, register 1. Why you would have two register 1s written to at the same time, I don't know, but hey, because they're different ports, and because although you wouldn't write to them at the same time, you still need an OR gate. So likewise for the read. So if you use this register 1, I've done it again, haven't I? It would have been better for me to swap the numbers on the damn things, wouldn't it? Yep, there we go. There we go. Where's the Tipex when you need it? So this is your the line for go read 1 on register port 1 for register 1. Okay, so well, this is all for register 1 in this column. So an instruction gets issued and it says, I want operand 1 I want to reserve operand 1. So this SR latch will go high and that Q will go high, just like with the write, but now this is for read. Therefore, on subsequent any subsequent operation, on a subsequent cycle, if any, coming down to here, these OR gates, if any other operation requests either on destination 1 or destination 2 to write to that same register, then because that's an OR gate there, and because it is going into this AND gate, and this Q is high for saying I have a read dependency, read on protection dependency on here, then the write after read pending line will go high. Hooray. So reads stop writes, writes stop reads. Now this was high, okay, all right, and there, let's say that for this particular register there was no write hazard going, write hazard line going. Therefore, it is you get the ORing of that in, and there's a go write here. This is the register select lines, okay, which go directly to the actually to the register file as the write enable and read enable lines. So let's say that we're clear to pull that go write line, okay. Then the first thing that happens is that comes down to here. It will, on the clock, it will clear Q, but remember I said it's on the go write signal in the original 6600. We're going to have to change this in our design. The go write signal comes in off the clock when the clock is on the low cycle, right? So it does not throw this and cancel that Q, right? So comes in here on that AND gate. This Q is set, the go write is set, therefore this AND gate goes high in that OR gate for all register 1 in this entire column. You remember this is for function unit 1, and below is for function unit 2, etc., etc. I'm saying then that register select enable line here for register 1 will go high, and you will be able to write to the register file from this result, which goes directly onto the port 1 write line. So you have 2 ports, write 2 and write 1. So that will be put onto the multiplexing bus for write 1. Yeah. When the clock goes high, this line still being set will trigger this AND gate, and that will reset this SR latch so that this Q output will be false. So it's one of the quirky things, there's fantastic things about the original 6600 was this use of the high-low clock, so you had a rising edge and a falling edge triggering. Amazing that they did this entirely with transistors. Just so deeply impressive. So that on the falling edge, you get the Q ANDing with the go right signal to produce the register select line, and then on the rising edge of the clock, that go right line, which still stays valid for an entire high-low cycle of the clock, will reset this one, and that will indicate that the result has been written. And in the case of this one, this SR latch, or whatever it is, this SR latch, because we're talking about go right 1, this SR latch will go low. And if that one happens to be low, we get the reset, and the computation unit goes back to its original state. So likewise, exactly the same thing for these ones. Okay, now so when you get the go read again, it starts on the clock low first of all, which ensures that the SR latch stays, Q output stays high, which results in the read enable register select line being enabled, and that will result in the operand 1 or operand 2, whichever bus in which you're saying. So operand 1 read bus, operand 2 read bus will result in the correct thing being multiplexed onto the incoming operand thing, and again. Because you got that go read will go low, and on the subsequent cycle, and the latch will be go read reset. Yes, that will go low, and the operand will be latched in there. Phew. So I'm reasonably confident that these diagrams are okay, apart from if I messed up that thing. Where's the DebX? Again, and just finally remember, when that goes low, when that goes off, then this AND gate can never go true. Therefore, this OR gate will likewise not go true. Okay, assuming that this one is not true as well, and therefore, should another operation come in, no matter the fact that these OR gates for operand 1 or operand 2 read, that will not result in read pending being triggered for this function unit, and the operation will be permitted to proceed. So that's how you do this thing. It's basically if there is no read pending on any of those things, then the operation may proceed. Is the basic logic. It's just ridiculously sophisticated, but honestly, it's simple. It's deceptively simple. The amount of logic required is extraordinarily minimalistic, but the consequences The implications are that you have this register renaming capability. You have full read after write after read, hazard protection, latching on results, everything that's needed to do a full multi-issue out-of-order execution engine. And the reason why it's multi-issue capable is because everything is done on a bit level. All of the register numbers are done via an unary matrix. So this is an unary thing. So you can fire, in this row you can fire a thing, but you can fire multiple registers requests simultaneously, which you cannot do with a binary system unless you have multi-porting and content addressable memory. This does not require content addressable memory and thus is much more power efficient, despite being enormous. 50,000 gates for which cells when you multiply them up. And if we use just D flip-flops, it will be 250,000 gates for these dependency matrices. So we're using SR latches. I think that's it. Gotta go and upload this on YouTube. Thank you very much.